Hi, everybody. I'm Bistra Dilkina. I'm really happy to be here. I'm an associate professor of computer science and industrial system engineering at USC. And I also co-direct the USC Center for AI in Society. So a lot of my work focuses on the integration of machine learning and optimization, trying to get more effective solution methods that combine the strengths of both. And I also have a strong interest in real-world applications, in particular ones that have something to do with social good and social impact of environmental sustainability. I'm also the site lead and a co-PI for the NSF AI Institute for Advances in Optimization, AI for Opt. So we are kind of a group of faculty across Georgia Tech, Berkeley, and USC, focusing at, again, that intersection between AI and discrete optimization, basically trying to create the new big step change in our ability to solve complex optimization problems by bringing machine learning in an integrated way. So in my work, I have two kind of streams of work. One is infusing discrete optimization with machine learning. So how can we help optimization solvers do better? And the other one is infusing machine learning with constrained decision making. Basically, how do we develop learning methods that incorporate the combinatorial decisions that they inform downstream? So, for example, in augmenting discrete optimization with machine learning, I have worked on developing methods, ML-guided methods for graph optimization, a large body of work on improving mixed integer programming solvers, which I'm going to share with you today, and more recently, multi-agent pathfinding, basically planning algorithms, again, augmenting those with ML-guided components in order to improve the state of the art. In the other direction is basically focusing on the fact that many predictive models are in fact a first step in a pipeline where we are, let's say, trying to predict the prices of something or the demand for some good in order to then feed those predictions right into some kind of a resource allocation problem. And so thinking about the fact that we have this full pipeline of predictions and then optimization is important in order to make the overall effectiveness of that pipeline as good as possible. What we want to do is at the end to have the best decisions possible. So we basically designed this framework called decision-focused learning, where while we are training our ML methods, we are focusing on the decision loss. How bad will the decision, the downstream of optimized decisions with respect to predictions be in relation to if we had perfect predictions? And so for that, we have done several methodological developments using this decision-focused learning paradigm for linear programming as a modular optimization, then designing a methodology where we could integrate, in fact, whole mixed integer programs as a layer in our deep learning architectures when the downstream task is, in fact, the MIP. And then applying some of these methodologies to real-world applications in tuberculosis, resource allocation, and in predicting wildlife trafficking routes. And then one of the most recent work is also using this kind of differentiable optimization approach to actually think about how to predict and solve mixed integer nonlinear programs. Where you might have a problem instance for which you're predicting something that have a non-linear constraint problem, and you can again do this end-to-end learning optimization. But today I'm going to focus on the left side, which is infusing discrete optimization with machine learning. And what is the motivation behind that? Obviously, combinatorial algorithms have been a very active research area for many years. We have a lot of sophisticated subsolvers, MIP solvers, all kinds of solvers. And so why are we kind of like not in a status quo in a good place? Well, the problems we need to solve continuously increase in size and complexity. Every time we get new applications and have new combinatorial structure, we often need to kind of invent new heuristics or specialized solvers for them. So there's continued need in trying to improve our combinatorial solving methodology. And my approach to this is to actually think of this as an opportunity to integrate machine learning, which will make our solvers more adaptable to these changes. So today, as I said, I'm going to focus in the context of mixed integer linear programs, or MILP, or MIP for short, where we have a mixture of continuous and discrete variables. We have linear constraints and linear objectives. So this is a kind of a mathematical optimization framework that is very flexible and broad. It can encode many real-world applications, from energy transportation, material discovery, etc. And in fact, it has a huge industry component. I mean, there's like so many companies that under the hood use MIP as a way to solve their resource allocation problems. And so that is why the kind of like commercial or industry strength solvers are very well developed. We have branch and bound solvers like Guroki and Cplex, which have been deployed for many years, and a lot of different heuristics. However, all of these solvers are in a sense like a kind of a one-fit-all method framework, where we are hoping that it will scale up to the particular industry problem that we have. However, in many, one thing that drives this research about using ML-guided solvers comes from the realization that in the real world, a company usually has a particular combinatorial problem they're trying to solve, such as routing their trucks to deliver goods, that they're repeatedly solving over and over again with just different data. So in a sense, we don't have like a particular problem type. We actually have a distribution of many instances of one particular problem type. And so that basically leads to the idea that what we really want for a particular client or a particular company for a particular problem is to really learn to solve very well that particular distribution. We don't need a solver that will be good at any possible NP-hard problem. We want a solver that is able to get good performance within the distribution for which is being deployed in specific context. So this is what they're going to try to attempt, to learn such policies tailored to a specific NP distribution, and in particular, instead of doing that once, design frameworks that integrate these ML-guided components in a way that when you get a new distribution, you can retrain it and get that boost performance. So the idea is that we can get better performance of a generic one-fits-all approach, like a generic branch and bound algorithm, and that you would also, by integrating this ML-guided component, you will have a framework where you would not need to have a hand-designed custom approaches to a new problem. As long as you can encode it into a MIP, then you can retrain our ML-guided MIP solvers. So, when I started on this kind of agenda of building ML-guided solvers in 2015-16, there was very little work. However, the community has been growing massively, and there's been a lot of different successes of how to think about where machine learning can help. However, I would say that the very first, way earlier, really a realization of treating combinatorial optimizations as data, essentially each instance is a sample in a data distribution, you want to learn something about it, was really in the area of using machine learning to do algorithm selection or algorithm portfolios, in which Kevin and Frank both had played a big hand in things like SMAC and AutoML, Satzilla, and so on, right? So most of these approaches were using machine learning to kind of select an algorithm or tune the hyperparameters of an algorithm. So in this more recent body of work, what really has happened is that we are, instead of thinking of still the algorithms and solvers being like a black box designed by like very sophisticated mathematically guided approaches, is to actually open the solvers and think of them as more a white box or a gray box, where we basically redesign internal components of the solvers with this kind of ML perspective in mind. So for example, branch and bound solvers, which do a research in the possible space of solutions, where you would branch on a variable at every node of the research and then solve a subproblem, solve LP, choose the next node to expand, etc., which are kind of the bread and butter of solving combinatorial problems both in SAT and in MIP and in many other combinatorial domains, have a lot of heuristics built into them. Although the completeness of the search doesn't is always guaranteed, how you choose where to branch or which node to expand is highly impactful on the solving time. And so people have learned proposed ML-guided learning methods on how to choose these branching decisions, how to choose which cuts to add, how to choose which primal heuristic to run or which nodes to expand, with great successes showing that a lot of these like tried and true developed over the years, like industrial strength heuristics that are already in solvers like Simplex and Skip and Gurobi could actually be outperformed by doing this distributional learning. Okay. And so beyond that, there's also been work on using ML for other solver or algorithms frameworks beyond research, so more in heuristic search, such as large neighborhood search or solution prediction, as well as machine learning for other combinatorial problems like graph optimization, TSP, SAT, etc. So, but as I said, today I'm going to show an example of some of the work we have done on improving solving problems specifically for this mixed integer programming. And at the core of the two papers that I'm going to try to cover today is this use of contrastive learning. So this is kind of like the newest work in as I said, quite a long sequence of papers that has continuously improved this ML-guided ideas in deep solving that I really feel has a very unique advantage over like the supervised kind of imitation learning perspective that most of the papers have done. I don't see what you showed me.
30 minutes.
So that 30 minutes left.
I think you can talk for 30 minutes.
But since I got talked for 10,
There you go.
so the first thing I'm going to talk about is a heuristic large neighborhood search method for MIP and how we improve the existing frameworks for this LNS, the search methods for with contrastive learning. So this is joint work with my former PhD students Darwan and Aaron, who both recently graduated, and our collaborators at Meta AI Research. So what is large neighborhood search? Large neighborhood search is a local search method that is extremely effective on very hard problems, for which you basically cannot really afford to run branch and bound. So, but also for problems where finding feasible solutions is not very hard, because you have to start with an initial solution that's feasible, and then what you do is you take part of the assignments, you unfreeze them, or what's called you destroy them. So you take some subset of the variables, you destroy the assignments, and then you re-optimize just that sub-problem while keeping all the other variables the same. Now you have found a new solution that is possibly improved or the same as before, is like unfreezing those variables in hell, and you go back and you keep on iterating, moving from one solution to the next, every time choosing a new destroy set to re-optimize. And so a lot of work in many different specific combinatorial domains has gone into what does this neighborhood look like? How do we choose which variable to destroy? Like if you open like supply chain, industrial system engineering journals, there's full of specific papers on LNS with different heuristics. So this destroy operation is really like a very important component. And so this is where we identify with this perfect opportunity for ML, where instead of having a custom heuristic designed by an OR PhD team, we could actually leverage learning. Okay, so what is a destroy step? So given an ILP and the current best solution, we are going to choose at most k variables to unassign and to re-optimize them while fixing the rest. So what would be the optimum set of k variables to actually unfreeze and re-optimize? You can actually specifically formulate that problem mathematically as another MIP. And in fact, that's what the paper by Viscetti and Lodi did in 2003, and they call this a local branching. Okay, And so in local branching, we basically have the original MIP, which is our objective, our constraints, our variables. And then, but we also have our current solution, X star. And we're basically saying you're allowed to flip the zeros to 1 or the 1s to 0 up to k times. And you're trying still to, while allowing for this up to k switches, you're still trying to minimize the original objective. So find the k variables that you would flip in order to improve as much as possible the objective. So yeah,
It's nothing my optimal.
it's optimum within changing up to k. Yeah. So it's fine.
This doesn't imagine that you're going to do this again in the future.
Yeah.
This is
So
one
that's
step,
the
okay.
one-step local optimum. Yes. And so, but solving obviously this MIP is just as large as the previous one plus one constraint, so itself is very hard. So you generally you cannot afford to keep on doing that at every iteration, because if you could do that, then you could just branch and bound for your original problem. So this is kind of a very nice kind of theoretical framework, but it's not really a heuristic you would deploy in practice with an MMS. But what we can use this for is to generate this optimal, very good destroy sets to imitate or to learn to predict. Okay. So this local branch heuristic is, in hindsight, it gives us the best possible one-step choices, but it's so expensive that you would never want to do it. Okay. So so one thing to do is to try to basically figure out how to predict this. And so there was an early paper by Google DeepMind, which basically formulated this problem as an imitation learning problem. So they collected a lot of these local branching ILP solutions offline, and then they trained an imitation learning pipeline that basically learns to predict for each variable whether it should be in this destroy set or not. So once this training is done based on imitation learning, at test time, you basically sample the neighborhoods based on these predicted scores for each variables of how likely they are to be in this destroy set. So without all the prior work, it's like this is like code jump into this field, but still. So this is in line with a lot of the other work, let's say branching prediction, so on, which also uses imitation learning, where we basically collect offline a bunch of, with a lot of computational costs, a lot of examples of what would be the best local choices, and then we learn to imitate. So what we brought to the table in this context is to really understand that basically, first of all, there could be many possible destroy sets that are almost equally as good. So learning to imitate just the one optimum solution that local branching ILP gives you is like gives you a very fixed small window into what good choices can look like. And then the other thing to understand is that the destroy set is actually a prediction over the whole set of variables. Like if you leave one variable out, the rest of them might not be a good choice without that also being frozen, right? And so then looking at just imitating a single solution, in particular imitating each variable, whether it's in and out, is not very useful in the global sense. Yeah.
Aren't you making implicit assumption that there is not a great difference in terms of the quality of the, let's say, quotes locally optimal solution that different good samples lead to? So in other words, he seems to be predicated on the assumption that it's enough to distinguish between bad samples and good samples, but between different good samples, there is not a great difference in the eventual quality that they lead to. Is it always true?
Well, we don't know, but I guess what we're arguing for is that moving away from a single best example to multiple good examples, and not only multiple good examples, but also contrasting good with bad examples, is going to give a more rich picture to the ML learning prediction than single imitation.
I like the idea. It was just a technical.
But it is, yeah, there is an assumption, and there's also what Kevin was trying to refer to is that like this is also we're imitating the single step best move, and obviously there's kind of like a sequential decision aspect large neighborhood search, where cumulatively you also don't know what really the best destroy set would have been, given the fact that you do it again and again and again, right? Which would suggest more of a reinforcement learning kind of approach. And in fact, there's a previous paper that I'm going to compare to, which did reinforcement learning for large neighborhood search. So, but quickly to explain contrastive learning, basically the contrastive learning idea comes from literature in computer vision, where you basically don't want to only show the model in terms of data of what's the right answer, but also give examples of what bad answers look like. In the example, predicting whether an image is a cat or not, you're going to give it a bunch of images and say, yes, these are the positive pairs, which are the cats. You want to predict that a particular image is close to a cat when the cat is a positive example, but you also want to make sure that the representation is as far away as from images of dogs so that you don't confuse the two classes. Okay, so what does that mean in real world, right? We can understand what this means for images. They're both images of animals. They're kind of focused on the ears and the eyes and the nose, but so they're easy to confuse, and so that's why you give them as positive and negative examples, where you really wanted to figure out what are the distinctive features of what a cat image would look like. But the idea again is that you would have a stronger signal instead of just giving positive examples, by giving positive and negative examples and trying to really force the model to represent the samples in a feature space to be closer to the positive, while making sure that they're as far away from the negative as possible. And so before this work, there was already some existing work on starting to think about using contrastive losses in combinatorial settings such as satisfiability, but not in. Okay. So how are we going to apply this contrastive learning paradigm to mixed integer programming? Well, so here we start with our distribution of linked instances. We find an initial solution, which is a 0-1 vector if it's a binary MIP for now. We use our local branching ILP offline to collect data of these best moves, which is the same what the imitation learning paradigm would have done. But instead of just finding that best ILP solution of the local branching formulation, we collect training data which has both positive and negative examples. And now in a second, to give you a little bit more detail about what positive and negative means in this context, and that's kind of the crux of making this applicable and effective in this context. And then we choose the destroy set, whichever the best destroy set was found by the local branching. We re-optimize the submit, we move to the next complete solution, and we go back. And we keep collecting data over and over again over multiple steps of the LMS and over multiple instances. And this way, we create this data set that then we're going to use to train with our contrastive learning paradigm. Okay. So what makes for good positive and good negative samples here in the context of MIPS? So what we decided to do in terms of positive examples, instead of just keeping the optimum local branching solutions that was found, to actually get the trace of continuously improving solutions and take the optimum and the suboptimum solutions that are closest to the optimum that were found during the branch and bound search. So we run 1 hour of skip search for every LMS move. I mean, that's like a huge computational investment. So I have to be very upfront about these methods do require a lot of offline computing. But the idea is hopefully that they will generalize very well. And so within this 1 hour, we basically collect all the improving solutions. We take the top whatever P solutions that are closest to the ones found within 1 hour. And these become our positive samples. So all 0-1 solutions found by local branching with improvement that's better than 50% of the best solution found, up to 10 solutions is basically our kind of positive solution cutoff here. So in a sense, if if there's not enough good solutions, we often have less than 10 positive samples. Okay, so it really depends on where we are in the search space about how many good solutions we might find here. Okay, and so the negative samples, the idea again here, the key thing to realize is that what we really need to predict is we need to predict the destroy set as a whole. Okay, so there's not an individual variable, because if we miss some variables in the destroy set, then the rest of the variables might not be good enough. So even if they are frozen, it's still not useful, right? So we want to really make sure that to compile, to create a set of negative examples that will tease this out during the contrastive learning. So in order to do that, we took every positive sample. Again, a positive sample is a 0, 1 vector that says, is the variable in the destroy set or not, right? And we perturb it just slightly. We replace only 5% of the variable in that positive destroy set that we found in the skip search. Then we solve the LNS subproblem to see how improving that perturbed set is going to be. And if we find that that perturbed set, although it has changed only by 5%, actually gives a very small improvement in terms of the new incumbent solution, then that's a negative sum. So basically, we're finding destroy sets that look almost the same as the positive ones, and yet give a much smaller improvement. So they're like sets that look like the good ones, but yet don't have the same reward. And so obviously this is sometimes hard to find, so you might need to perturb it more than 5%, up to 10, 20, 30, and so on. But the idea is that often we actually find negative examples that are very, very close to the positive ones. Okay, so now what we're trying to really do is to trying to make sure that the model has these very close samples to each other, and we'll learn to discriminate between them with a contrastive learning clause, which is basically looking at positive and negative sample, where a sample here is a destroy set. It's a 0, 1 vector that basically specifies a destroy set. We have a set of features that represent the need to be solved and the current search state. And we want to learn a model such that given those features predicts pi of x, which is again a 0, 1 continuous vector that says how likely each variable is in the destroy set. And we want the proposed destroyed set by the model to be close to the positive examples and to be far away from the negative examples in our data, right? So moving the kind of the prediction away as much as possible from those small improvement destroy sets. And this pi of x is going to be our neural network that, given the feature, is going to predict these destroy sets. So what is our learning architecture here? So it's by now kind of a standard practice in the ML guided MIP solving community, but also it's used in SAT and other combinatorial problems, where we represent the combinatorial instance as a bipartite graph of variables and constraints, where each constraint is connected to all the variables that appear in it with a non-zero coefficient. And so basically this becomes a graph, a bipartite graph. And on top of this bipartite graph, we create a graph convolutional network, which basically we're going to have features on the variables, features on the constraints. They're going to pass this information between each other to get an encoding, a representation layer from which we're going to make the final predictions. So the variables that we use are, again, quite established within other ML learning tasks in MIP, such as the objective coefficients, the number of constraints each variable participates in. Here, because we're in LNS, we have the LNS specific features that refer to the most recent best found solutions in the LNS iterations, and constraint features like the number of non-zero coefficients, average coefficient values, etc. So all of these are kind of well established different features that have been shown to be very effective. And so what we do with this bipartite graph, we essentially have a message passing architecture where these original features are passed embedded from the variables to themselves, and then through the edges to the constraints and back to the variables. So this architecture is essentially kind of a GCN, but with attention, with 2 rounds of message passing, which at the end has basically a vector representation for all the variables in the problem that gets then passed through a final embedding in a sigmoid to get this output prediction which is a 0-1 continuous vector for all the variables in the problem, that essentially will be interpreted in our setting as a prediction of whether that variable should be in the destroy set or not. Okay, final output is the scoring, indicating how promising it is to select each variable for the destroy set of the LNS. So at this time, what we're going to do is we're going to have started our mean, have our current incumbent full solution, compute the features. Many of the features are essentially features that are computed only once at the beginning of the full bit, and some dynamic features based on the previous few solutions. And then we're going to predict this phi, choose the best. At this time, we're going to choose really the k variables with the max scores from our ML model and choose them as being the destroy set for our LNS bit. Okay, so let's see how this works. In our work, we have evaluation of our multiple domains. Here, I'm just going to show you two combinatorial domains, the weighted minimum vertex cover and the combinatorial functions domain, where we are talking about 1,000 variables and more than 65,000 constraints, or 4,000 variables and 5,600 constraints. And so we are going to also test the generalization from smaller to larger, where we train on these smaller instances, and then we just deploy the model to instances that are twice as large as the training ones. So as baselines, as I said, we're going to compare to vanilla branch and bound, previous work that's using imitation learning, and previous work that's using reinforcement learning for exactly the same task, predicting this destroy set in the context of large neighborhood search. So this is already on top of quite rigorous ML guided work for large neighborhood search for me. And random is where we randomly select a set of variables to destroy each step, which surprisingly works very well in many settings, and a heuristic that we proposed in our earlier work at CPOR. So here you can see the performance in minimum vertex cover on small and large instances. In purple is our contrastive learning. In pink and blue are the two ML guided previous best baselines, and you can see how large the improvement is over those. And in particular, in fact, that improvement is even larger when we generalize to large instances. Similarly, for combinatorial auction, again, the learning baselines of reinforcement learning and imitation learning can be dramatically outperformed by doing the contrastive learning, both in small and large instances. So this is basically, to read this is runtime over seconds versus primal gap. So this is how fast we're closing, we're improving the primal solutions. If you take the area under the curve, which is basically what's called in MIP the primal integral, and it captures in a single value kind of the anytime performance of the solver, how quickly it's generating better solutions. So here, this same plots, but in bar charts, show the primal integral over all of the test instances, showing the dramatic improvements that contrastive learning can bring to the table over baselines that are not ML guided and the best existing ML guided, both in terms of imitation learning and reinforcement learning for this task. And again, the generalization in terms of from small to large performances is really, really good for these ML approaches. So in this context, we've shown that we can have up to 1.6 speed up for improving solutions in LNS. And in order to convince you that this contrastive learning is indeed a good framework, I want to show you another setting in MIP solving where we've shown, again, on top of already existing quite strong ML guided work, how we can bring even stronger improvements by leveraging contrastive learning. Here, this is in the context of backdoor prediction. So backdoors is a basically concept saying that in combinatorial problems, you might have a small set of variables, which in a sense hold the key to solving the problem. If you assign those problems, then those variables and the rest of the problem can be, the rest of the variables can be assigned by propagation. And if we could possibly find that small set of variables, then the problem will be solved much faster. Obviously, the question of finding those small set of key variables is itself actually harder than solving a problem, the original problem. So usually it's a signal to complete. But in practice, we have shown that a lot of real-world problems have that structure where you might have a very large problem, and yet there's a very small set of variables where really once you assign those, the rest of the variables get propagated through the constraints. So this has been shown both in terms of real-world problems encoded that satisfy ability instances, for example, in chip design, etc., as well as real-world instances encoded as mixed integer problems. So this is actually work that I did in my PhD a long time ago. So it was really fun to go back to it. And again, as I said, people have shown that backdoors exist, but yet we haven't really found a very good way to operationalize them. The fact that we know they exist hasn't really significantly helped us in building better solvers for real-world problems. So here the idea was, well, if we know these small combinatorial structures exist, can we get an ML model to tell us which these key variables are, to recognize them in the problem structure? Then we can tell the solver to branch on those variables first, and then hopefully have that speed up that theoretically we have hypothesized exists. Okay, so in earlier work in CPO1 2022, we attempted to do that, to design this methodology for learning pseudo backdoors for mixed integer programs. We worked very hard to try to get a learning architecture that works well and collected data on existing backdoors on many instances. So the idea was we're going to predict these backdoors, a small set of variables. We're going to tell the solver at the root, only try to branch on those first. And once you finish branching on those, if you're not done yet, then continue with your usual heuristics. And we basically showed that, in fact, we can, in data collection, find those small sets with a lot of sampling of many sets, and sometimes we get lucky and get one that actually works well, but many of them obviously don't work well. So we spend a lot of compute power sampling many possible subsets of variables to find those good sets to imitate. So in an earlier work, we designed this kind of an imitation based approach where we would collect these backdoors, have a data set of good examples, and then we train essentially a machine learning model which, given a proposed backdoor, will predict whether it's how good it might be for branching, and then based on that decide whether to use it or not. But this framework relied on the fact that we're going to sample backdoors by some external procedure, and the ML model just basically decided is it a good one or not, but was not able to actually generate backdoors itself. In this new work that I'm going to show now, we're actually generating the backdoors the same way we're generating the destroy sets in the LNS that I showed you earlier. In another related work, we actually designed a Monte Carlo tree search approach, which for sampling backdoors, which we showed is much better than the randomized sampling we had done before. But this is not about predicting, this is just basically a method for collecting backdoors, which is extremely expensive, but it allowed us to, again, show that we can find good backdoors, even for instances for which sampling had not found good backdoors before, by leveraging the fact that we have a smart reward on the Monte Carlo that guides the Monte Carlo research. Now I'm going to combine these two ideas together with contrastive learning to show you our newest results. So here we're going to use these contrastive laws as well as get much better training data by using the Monte Carlo research idea from the AAAI paper in order to get the new state-of-the-art in backdoor prediction. So the framework is very similar. We're going to have a mid instances. We're going to encode it as a bipartite graph. We're going to have a graph attention network that's going to predict a 0-1 vector that's going to tell us whether a particular variable should be in the backdoor or not. And we're going to train this graph network using contrastive laws by offline collecting a lot of samples, positive and negative samples, which in this case will correspond to backdoors, right? So we're going to collect sets of variables, some of which are going to be good backdoor sets, meaning they're going to result in speedups, and some of them are going to be bad backdoor sets, meaning that they're going to not result in speedups. And so again, in terms of data collection, the point is how do you design these positive and negative samples? In our case, we are using the Monte Carlo research to sample the positive samples. And for negative samples, we are basically also using the results from the Monte Carlo research, but just choosing the ones that actually resulted in the longest runtime out of the 50 top most promising backdoors that the Monte Carlo research found. So again, here, these are essentially samples that are almost positive, but not good enough to make the positive sample set. Sorry, I'm rushing because I know that now I'm over time. I don't have my glasses on, so I don't see what you're showing me, but 2 minutes according to my.
Wrap it up, you're starting to
Yes.
get into your questions, so.
Yeah. So just quickly, I guess this is kind of the last slide of this, just to show the effectiveness of the contrastive learning versus, again, the usual supervised learning. Here we have 6 different domains. 4 of them are pure binary, 2 are like mixed integer with both continuous and binary variables. And you can see in this bar chart, basically, this is the improvement over Kurobi. Kurobi is like the absolute state of the art in MIP solving right now. It's a really, really strong solver. And yet we're able to improve the performance by sometimes more than 50% over Kurobi by using this ML guided backdoor prediction. So this is a real fit. A lot of the other work that we've done on ML guided MIP solving that requires kind of white and gray box access to solver has had to be in Skip, which is the only open source solver, but it's significantly slower than Kurobi, right? So it's kind of, people can argue like, oh, it's easy to improve Skip because Skip is not commercial strength, but the problem is that Kurobi doesn't give you the access in order to modify things, so we are forced to use Skip. This prediction is very nice because we are predicting the backdoors on the top of the root node, which means it's a strategy that applies to Cplex, Kurobi, Skip, everything, right? And yet even though Kurobi is industry strength commercial solver, we are able to actually improve by 10 to 15% by using this ML guided solver. And our previous approach had successes, but also on some of the domains doesn't do very well. I'm going to skip that. So in conclusion, basically, I have shown you how contrastive learning has dramatically improved the state of the art already on top of the improvements that ML-guided approaches have brought to the MIP solving community. And I really believe that as a framework, it's something that's very useful to think about. In fact, we have a newer paper on contrast on another task. And the key idea is that really in a lot of the MIP solving components we need to do, we are predicting sets. We are predicting the destroy set in LMS, we are predicting the backdoor set in the backdoors task, or we are predicting a set of hyperparameters for the configuration side. And so the contrastive learning framework allows us for a way of thinking how to show the model both the good samples, which we can imitate, but also the bad samples that are just slightly different from the positive ones, and yet have a much smaller reward than the positive ones. So we have shown, as I said, this in 3 different settings in the MIP world, from LNS to backdoors to predict and search, and some of our newest work also does this for hyperparameter configuration and multitask representation learning. And the core of these big improvements is really leveraging this contrastive loss and really understanding that we're doing set prediction as opposed to a single variable prediction here. I'm going to stop here. I was going to talk about the benchmarks and data sets, but I'm going to, I guess, just say we have a new paper on arXiv in which we have finally released something that we've been working on for almost more than 2 years, called distributional MIP, where we are trying to establish kind of for the community a set of benchmarks of problem domains and problem instances that can be used to as a starting point for all this ML guided work, where we can compare on the same hardness levels and the same generators. So if you are thinking about doing this kind of work, check out.
Thanks very much. 2 remarks. First of all, I realized you just started talking before I had a chance to introduce you, so I didn't get to tell everyone how awesome you were, but that wasn't because I didn't want to introduce Bistra. I think she did a pretty good job of telling you about her background, what she's done. But let me just sort of say what I would have said in the introduction is that this area of machine learning plus combinatorial optimization, I think, is really poised to be a growth area now. And I think we're starting to see the point where search is getting rediscovered as a core problem in AI. Now that we're realizing that the core computational object might be a call to an LLM rather than just being a sort of access to a Turing machine. And so I think we're poised to see this sort of fusion in ML and optimization really growing. And Bistra is one of my favorite people in the space. So I'm really happy to got a chance to hear from her today. Why don't we take a couple of questions and then we'll go back to our last talk.
I want to ask about the framing of contrastive learning. Usually people do that when they don't have labels for, okay, I have ImageNet and I want to separate cats from dogs without labels for what is a cat and what is a dog. Here you do have labels for like what is good and what is bad.
Yeah.
But you're still using contrastive, which seems a little strange to me. Like, why don't you just classify good versus bad?
What would that mean? Basically, again, part of it is because we are trying to think about this as a set. This is a vector of, let's say, variables that I'm trying to predict.
But you're doing a linear function on that variable anyway, which is the other question I wanted to ask. So you're not, your prediction is just, is this variable good or not? You're not doing any joint modeling in there. Your A model, like the model proposing is different from others. Contrastive side is.
Yeah, I guess it's still doing just a dot product, right? But it is it's doing like the call like e to the dot product for a specific prediction, right? So you're aggregating these losses over for each instance, and for example, for each LNS move, for that particular vector, I'm summing it up, but I'm penalizing for that positive sample divided by the negative sample for that particular instance. So in a sense, it's coupling the positive and negative examples for each instance, for each sample in our data set. Trying and in that it's giving a signal about the fact that we want this to be closer to the correct set of variables versus the slightly perturbed set of variables that actually results in that. So very different if we were just doing the imitation learning where there's no negative examples, right?
Oh yeah, having the negative examples feels like it's a big improvement over not, for sure.
So what are you
But-
proposing to do them somehow in a different way?
Yeah, I don't know if it would be better. It's just if I were doing this and you said, here, I have these positive examples, these negative examples, I wouldn't have used that loss. Because, yeah, it just doesn't feel like I don't know what the right thing to do would be. I guess if you trained a classifier specifically for these positives and these negatives, and you introduce an issue of having to choose like a threshold, and maybe this kind of automatically gives you a threshold.
Exactly.
But it still feels.
It also removes the fact that like you would have to have like some kind of a separate mechanism which gives you the candidate when then you're going to classify as a positive or negative. Versus here, we want to train a model which would generate out because there are 2 to the n possible predictions. Right? It says the model itself is generating that 0, 1 vector.
But
otherwise, you would like have some other thing that generates sample, and then it would just simply learn to predict whether it's a good one
So
or a bad
the
one.
thing I'm concerned about with contrastive learning, and then I'll stop talking, is if you have positives that are different from each other, or like you have negatives that are very similar to your positives, but also presumably you sometimes have, oh yeah, this is a good set and this is also a good set, and they're different from each other, right? Then this linear function of is this variable good or not, like it's trying to make those two things seem similar in a way that I don't know exactly what to do, but it feels very strange to me.
It's not I would say it's not maybe not the ideal solution. In fact, I've been describing this problem to a lot of deep learning ML experts, is like what we really, the ideal thing is that we want a model that is really designed for set prediction. And contrastive loss is just like something that's slightly better than just treating each variable essentially individually, what imitation learning is doing, right? So it's like I could literally be predicting each one of them as its own thing, but it's not yet actually leveraging, solving the true problem, which is that we want to have something that really predicts over sets.
Yeah, I wondered why you were just doing regression, right? You could just predict the quality of the set.
You still want to be able to generate set directly from the model. Because there's exponentially many sets to the end.
Sure.
So even if you have the best possible regressor, right, that will give you how good it is.
Yeah.
Who's going to do the sampling? Who's going to give that regressor what you're going to evaluate? If that sampler never samples any of the good things, the regressor will still tell you it's a bad one, but there's 2 to the end of that. So you want the model to actually just try to predict the set directly, not predict how good something is that somebody else has to sample. Because there's exponentially many of them, then you're relying on a sample.
One last question from somebody else. Yeah.
Does your runtime include the training time of the neural network?
Of course not, because like you're training offline on a distribution of instances that's training instances, and then at test time, let's think about Amazon. Amazon has historic data from the last 1 year of their deliveries. They use these routing problems, they train offline this methodology, and then on the next day they get a brand new instance. At that time, they're just doing inference.
But I think the neural network might be distinct for different.
For each client, as I said, like for each client, let's say again, Amazon is training ML graph attention network that is very good for predicting the backdoors for their routing problems in Los Angeles, right? It's one particular distribution. They invest in the compute time. They have the historic data from the last 2 years of Los Angeles deliveries. Now they have a model that they can run each day for the next whatever 2 3 years in Los Angeles, and it works really well. And at that time, at test time, they're just solving the problems really fast when they have to make decisions on real time or in the beginning of the day. So they don't have to retrain every day. They can train once within the distribution, as long as there's no big distribution shift. It's still be useful.
All right, let's leave it there. Thanks, everyone.